directly go to the topic. Already we discussed the introduction part of soft computing, types of soft computing, and various classifications of soft computing. Introduction to artificial neural networks and supervised learning network model also we discussed. Now let us we go to the important topic, supervised learning network 2 and associate memory network that I told in the last class. This is the topic today, supervised learning network 2 and associate memory network. I will share my screen also. This is the topic, supervising learning network 1 and associate memory network. This is the main topic in this presentation. Okay, so let us share my screen for the comfortability. The unit structure is like this: objective, backpropagation network, radial basis function, time delay neural network, functional link network, tree neural network, wavelet neural network, overview of associate memory, training algorithm for pattern association, auto association memory network, hetero association memory network, bidirectional associate memory, Hopfield networks, iterative auto associate memory network, temporal associate memory network, and then review questions. The object is what we have to meet here to understand the backpropagation networks and real-time network applications. The first objective is objective 1, to understand backpropagation networks used in real-time applications. The objective 2, theory behind radial basis network and its activation function. Objective 2 is theory behind radial basis network and its activation function. And objective 3, special supervised learning networks such as time delay, neural networks, functional link networks, the neural networks, and wavelet neural networks. Objective 4, details and understanding about associate memory and its types. Objective 4, details and understanding associate memory and its type. Objective 5, the fifth objective, help field networks and its training algorithm. Help field networks and its training algorithm. Objective 6, an overview of the iterative auto associative and temporal associate memory. An overview of the iterative associate memory, auto and temporal associate memory, backpropagation networks. It is applied to multi-layer feed-forward networks consisting of processing elements with different activation functions. The networks associated with backpropagation learning algorithm is known as backpropagation networks. It uses gradient descent method to calculate error and propagation back to grain unit. The training backpropagation algorithm is performed in 3 stages: feed forward input training pattern, then the second one is calculation backpropagation of the error, Third one is weight updates. Architecture and backpropagation network. Okay, like this. Input layer, just examine the diagram. Hidden layers, observe the input layer section, observe the hidden layer section, observe the output layer, difference in desired values, backpropagation output layer, like this. Examine the different layers here. Architecture of backpropagation network you can observe very clearly. The first one is a backpropagation network. Neural network is a multi-layer from a feed-forward neural network consisting of an input layer, a hidden layer, and output layer. Propagation neural network is a highlight sentence, very highlight sentence in this topic. A propagation neural network is an important question. Okay, for the examination point of view to get a good marks. A backpropagation neural network is a multi-layer feed-forward neural network consisting of an input layer, hidden layer, and output layer. The neurons present in the hidden and output layers have activation with always value 1. The bias also acts as weights. During the learning phase, signals are sent to the reverse direction. Sent in the reverse direction during the learning phase. The output obtained can be either binary or bipolar. Okay, radial basis function network. The radial basis function is classification and functional approximation neural network. It uses nonlinear activation function like sigmoidal and Gaussian functions. Since the radial basis functions have only one hidden layer, the convergence for optimization is much faster. The architecture consists of two layers. The output nodes, the second point is the output nodes from a linear combination of the basis functions computed by means of radial basis function nodes. Hidden layers generates a signal corresponding to an input vector in the input layer and corresponding to the signal network generates a response. Here the layers like this. We examine the layers of the architecture of radial basis functions. Architecture of radial basis functions, we examine the various layers. Input layer, hidden layer, output layer. Architecture of radial basis functions. Time delay neural networks. Time delay neural networks are basically feed-forward neural networks, except that the input weights has a tapped delay line associated to it. In time delay neural networks, when the output is being fed back through a unit delay into the input layer, the net computed is equivalent to an infinite impulse response filter. A neuron is with a tapped delay line is called time delay neural network unit. And a network which consists of time delay neural networks units is called time delay neural network. Applications of time neural network is speech recognition. Applications of time delay neural network is we can understand these concepts very well. That's enough. Okay, and diagram. Concepts diagram about these two. Okay, once again I'm telling the backpropagation networks, radial basis function network, the concept diagram you can easily write it, and time delay networks concept and its diagram. Functional link networks. Functional length network is a specially designed high order neural network with low complexity for handling linearly non-separable problem. It has no hidden layers. This model is useful for learning continuous functions. The most common examples of the non-separable functions is XR problem. X sin pi x, cos pi x, sin 2 pi x, cos pi x, sin n pi x, like that. We can make all those excuse me, this in XR form into the summation y is equal to f of x. Okay, some XR line you can make it. All these functions are XORed in a output y summation. This is called functional line network model with no hidden layer. Okay, this is about functional link networks. Okay, just concept diagram about what back propagation networks. Okay, okay, back propagation network, and other one is radial basis function network. Radial basis function network. Time delay neural networks. Time delay neural networks. Functional link networks. Functional link networks. Next, tree neural networks. Next discussion is tree neural networks. These networks are basically used for pattern recognition problems. It uses multi-layer neural network at each decision-making node of a binary classification for extracting a nonlinear feature. The decision nodes are circular nodes and the terminal nodes are square nodes. The splitting rule decides whether the pattern moves to the right or left. The algorithm consists of two phases. The growing phase, a large tree is grown in this phase by recursively finding the rules of splitting until all terminal nodes have nearly pure membership, or else it can be split further. Tree pruning phase to avoid overfitting. Okay, so and of data, a smaller tree is selected or it is pure pruned. Okay, this is tree neural networks concept. This is the concept of tree neural networks. Just examine the diagram. Tree neural networks can be used for wave recognition problem. This is each and every algorithm has meant for solving some type of problem. Okay, so this tree recognition neural network is used for waveform recognition problem. This is the f1 of x less than theta 1, f2 of x less than theta 2, yes. No, f3 of x less than theta 3, plus c bar is equal to 1, no, c bar is equal to 2 conditions. This theta 3, yes, c bar is equal to 1, no, c bar is equal to 3. Binary classification break. Next step, the important one is wavelet neural networks. Wavelet neural networks. What are wavelet neural networks? These networks on wavelet transform theory. They are based on wavelet transforms. All of you aware about the mathematical wavelet transforms? Okay, here we apply the wavelet transforms here. In this network, we will apply the wavelet transforms. It is useful for functional approximation through wavelet decomposition. It consists of rotation, dilation, translation, and if the wavelet lies on the same line, then it is called wavelength instead of a neuron. Okay, the wavelet networks. We will use the wavelet transforms here. Okay, how we apply the mathematical model of concepts of wavelet transforms? Those concepts are same here. There is no difference. Application of wavelet transform theory here simply, and then okay, the its particular architecture or diagram. That's enough. This is a diagram. Wavelet neural network with translation, rotation, dilation, and wavelength. Just see the diagram. R1 rotation, T dilation. Okay, so and then coming into the translation. Okay, and wavelength. W is wavelength like that. Four block very simple diagrams there. You can easily write it on the exam. Just I want to see. So you want to see this diagram. This input X connected to the blocks, series of blocks, of course N, R1, R2, R3, like N. Rotation, D stands for dilation blocks. Okay, it is very important question for the exam, but you can write it very easily. Okay, and other one is okay. The translation part, other one is wavelength part, like that. Output. This is the thing. Associate memory networks overview. Associate memory networks overview. Associate memory networks. An associate first point, an associate memory is a content addressable memory structure that maps the set of input patterns to the output patterns. It can store a set of patterns as memories. The recall is through association of key patterns with the help of information memorized. An associate memory makes a parallel search with a stored data file. The concept behind this is type of search is to retrieve the stored data either completely or partially. Okay, this is the concept of associate memory networks overview. Associate memory networks overview, and that is about associate memory networks overview. Then you should know about what is unsupervised learning. This is the conclusion topic in this session. Unsupervised learning. What is this unsupervised learning? You have to see the structure. Introduction, fixed weight competitive nets, Mexicon hat net, Hamming network, okay, Kohaman self-organization future maps, Kohanan self-organization motor map, learning vector quantization, counter propagation networks, adaptive resonance theory network. In this learning introduction part, there exists no feedback from the system environment. W indicates the desired outputs of a network. The network by itself should discover any relationships of interest, such as features, patterns, contours, correlations, or categories, classification in the input data, and thereby translates the discovered relationships into the outputs. Such networks are also called as self-organizing networks. An unsupervised learning can judge how similar a new input pattern is to typical patterns already seen, and the network gradually learns what similarity is. The network may construct a set of axes along which to measure similarity to previous pattern, that is, to perform principal component analysis, clustering, adaptive vector quantization, and future mapping. For example, when net has been trained to classify the input patterns into any one of the output classes, say PQRSRT, the net may respond to both classes. P and Q are R and S. Okay, in the case in mentioned, only one of the several neurons should fire, that is, a respond. Hence, the network has an added structure by means of which the net is forced to make a decision so that only one unit will respond. The process for achieving this is called computation. Practically considering a set of students, if we want to classify them on the basis of evaluation performance, their score may be calculated, and the one whose sum is higher than the others should be the winner. The same principle adopted here is followed in the neural networks for pattern classification. In this case, there may exist a tie. A suitable solution is presented even when a tie occurs. Hence, these nets may also called as competitive nets. The extreme from these competitive nets is called winner take all. Okay? The name itself implies that only one neuron in the competitive group will possess a non-zero output signal at the end of competition. There exist several neural networks that come under a category. We list a few: MaxNet, Mexican Hat, HammingNet, Cohen's Self-Organization Feature Map, Counterpropagation Net, Learning Vector Quantization, Adaptive Resonance Theory. The learning algorithm is used in most of these nets is known as Cohen algorithm. In this learning, the units update their weights by forming a new weight vector, which is a linear combination of old weight vector and a new input vector. Also, the learning continues for the unit whose weight vector is closest to the input vector. The weight updation formula is used in Cohen learning for output cluster unit J is given as Wj nu is equal to some W theta whole plus A of x minus W theta J of whole is a formula. To understand only this formula, where x is the input vector, Wtj is the weight vector for unit J, alpha the learning rate whose values decreases monotonically as training continues. There exist two methods to determine the winner the J network during computation. One of the methods for determining the winner uses square of the Euclidean distance between the input vector and weight vector, and the unit whose weight vector is at the smallest Euclidean distance from the input vector is chosen as a winner. The next method is uses the dot product of the input vector and weight vector. The dot product between the input vector and weight vector is nothing but the net input calculated for the corresponding duster units. The unit with the largest dot product is chosen as a winner, and the weight updation is performed over in because the one with large dot product weight vectors both of the units of length. The next important one is fixed weight competitive nets. These competitive nets are those where the weights remain fixed even during training process. The idea of computation is used among neurons for enhancement of contrast in their activation functions. There are MaxNet, Mexican Net, HammingNet. MaxNet. The MaxNet is a service as a subnet of for picking the node whose input is large. Architecture of MaxNet. The architecture of MaxNet is shown in figure, where fixed symmetrical weights are present over the weighted interconnections. The weights between the neurons are inhibitory or fixed. The MaxNet with structure can be used to subnet to select a particular node whose net input is the largest. Testing application algorithm of MaxNet. Step 0. Initial weights and initial activations are set. The weight is set as 0 less than epsilon less than 1 meter, where m is the total number of modules. Let xi of 0 is equal to input to the node xi. wij is equal to 1 if I equal to j. wij is equal to minus epsilon if I not equal to j. Step 1. Perform step 2 to 4. When stopping condition false, step 2 to update activations of each node for j is equal to 1 to m. xj of n epsilon w. Okay, if f of xj od is epsilon of sigma I naught equal to j xk of old. Step. Save activations obtained for using in the next iteration for j is equal to 1 to m. Okay, xj of oid is equal to xj of mu. Step 4. Finally, test the stopping condition for convergence of the network. The following is the stopping condition. If one node has a non-zero activation, continuous else step. Okay, Mexican HetNet. Okay, Mexican Het network is a more generalized contrast enhancement network compared to the earlier MaxNet. There exist several cooperative neighbors. Neurons is close proximity to which every other neuron is connected by acceleratory links. Each neuron is connected over inhibitory weights to a number of commutative neighbors. Okay, there are several neurons on which conditions between neurons are not established. Here, in addition to the connections within a particular type of neural net, the neurons receive some other external signals. This interconnection pattern is repeated for several other neurons in the layer. Architecture of Mexican HetNet. The architecture of Mexican HetNet is shown in figure. This is the structure of Mexican HetNet architecture. Just observe the diagram. X minus 1, X minus 2, X minus 4, X minus 4. Xn1, Xn2, Xn3, like this corresponding weights. Neurons here are arranged in a linear order, having positive connections between xi and near neighboring units, and in negative connections between xi and farther away neighboring units. The positive connections region is called region of cooperation. The negative connection region is called region of competition. The size of the region depends on the relative magnitudes existing between the positive and negative weights, and also on the topology of the regions, such as a linear, rectangular, hexagonal grids. In Mexican hat, there exist two symmetric regions around each individual neuron. The individual neuron is denoted by xi. This neuron is surrounded by other neurons xi plus. xi1 plus 1, xi plus 2, xi minus 2, the nearest neighbors of the individual neurons. Okay. Hence, the weights associated with those are considered to be positive and are denoted as W1 and W2. The farthest neighbors M in the individual neurons xi are taken xi plus 3, xi minus 3. The weights associated with these negative and are denoted by W3. It can be seen xi plus 1 or xi minus 4 are not connected to the individual neuron xi, and therefore no weighted interconnection exists between these connections. To make it easier, the units present within the radius of 2 query per unit to the unit xi are connected with the positive weights. The units with radius 3 are connected to the negative weights. And the units present farther away from the radius 3 are not connected in any manner. Okay, the neuron xi. Structure of maxi hat. Flowchart of maxi hatnet. The flowchart of maxi hatnet as shown in figure. This clearly depicts the flow of process Mexican hat network. Start. Initialize the region of interconnected. Radius. Okay. Total iterations. Set initial weights. Set initial weights like this. Set vector activations at previous time step to 0. External signal is interrupted. Iteration count. Just observe the iteration counts in the flowchart. Compute input. Apply iteration process. Some current activations. Flowchart of Mexican hat. Very important. Okay. Algorithm of Mexican hat. The various parameters used in the training algorithm are shown in below. R2 is equal to radius of the region interconnections. Xi plus k and x of f minus k are connected to the individual units xi. For k is equal to 1 to R2. R1 is the region of positive reinforcement. Wk is the weight between xi and the units of xi plus k and xi minus k. 0 less than or equal to k less than or equal to R1. Wk is equal to positive. R1 less than or equal to k less than or equal to R2. Wk is equal to negative. T is equal to external input signal. X is equal to vector of activation. X0 is equal to vector of activations at previous time steps. Tmax is equal to total number of iterations, contrast, enhancements. Here the iteration is started only with incoming of the external signal presented to the network. Step 0, you can look about the step 0. Parameters R1, R2, Tmax are initialized according to the initialized weights as. Just observe the initialized weights. Wk is equal to C1 for k is equal to 0 to etc. R1. Wk is equal to C2 for k is equal to R1 plus 1 etc. R2, where is C2 greater than 0. They are the initialized weights. Initialize x0 equal to 0. Step 1, input the external signals as x is equal to s. The activations occurring are saved in an array x0 for I is equal to 1 to n, xy is equal to xi. Once activations are stored, set iteration count to t equal to 1. Step 2, when t is less than tmax, perform steps 3 to 7. Calculate the net input for I is equal to 1 to n. Xi is equal to C1, sigma k is equal to R1 to R1. Okay, xyi plus. Okay, some Ck is equal to R2, and next sigma is C2 is sigma K is equal to R1 plus R2. Like this, you can calculate for the net input. Step 4, apply activation function. Step 5, save current activations. Step 6, increment the iteration counter. Step 7, test for stopping condition. Observe the various steps. Once again, I am repeating. In step 1, input the external signal yes. In step 1, input the external signal yes. Step 2, when t is less than t max condition, what 2 steps you have to perform? Step 3, calculate net input. Calculate net input. Step 4, apply the activation function. Save the current activations. Step 5. Save the current activations. Increment the iteration counter. Step 6. Increment the iteration counter. Step 7. Test for stopping condition. Okay. The following is the stopping condition t less than okay some t of x. Then continue else stop. The positive reinforcement here, the capacity to increase the activation of units with larger initial activations, and the negative reinforcement has capacity to reduce the activation of units with similar initial activations. The activation function used here, the units xi at a particular time instant t is given by that function xy of lambda is equal to f of s of t. Okay, like this. The term present with the summation of symbol or weight signals that arrived from units, okay, alpha previous time step. Hamming network. The Hamming network selects stores classes which are at maximum Hamming distance from that noisy vector present to the input. The vectors involved in the case of binary and bipolar. Hamming network is a maximally likelihood classifier that determines okay which several exemplar. Learning of in depth regarding to Hamming network is very important. Next sequences. The Hamming network selects classes which are at maximum Hamming distance h from the noisy vector presented at the input. The vectors involved in the case are all binary and bipolar. Hamming network is a maximum likelihood classifier that determines which of several computer vectors the way in bracket the weight vector for an output unit in clustering net is exemplar vector or a code book vector for pattern of inputs which the net has placed on the duster unit is most similar to the input vector represented as an n triple. The weights of the net are determined by Example vectors. The difference between term and number of components and having distance between the vectors gives the measure of similarity between the input vector and stored example vectors. Is already discussed in the Hamming distance between the two vectors is the number of components in which vectors differ. Consider two bipolar vectors x and y. We use a relation x dot y is equal to a minus d, where a is the number of components in which vector agree, d is the number of components in which vector disagree. The value a minus d is the Hamming distance existing between two vectors. Since total number of components are n is equal to a plus d is equal to n minus a. On simplification, we get x dot y is equal to a minus d, x dot y is equal to a minus of, you can substitute n minus a there, then x dot y you can get 2a minus n. 2a is equal to just a small mathematical simplification here. 2 dot x dot y n plus a is equal to, we can write it very easily, 1 by 2 of x dot y, 1 by 2 of n, like that. Okay, so this is very simple simplification. You can easily do it. Just see this. I want to post here. Very simple, the mathematical calculation. This is the thing. Okay. On simplification, simple mathematical equations, you can get like this. On simplification, you can get from the above equations, it is clear to understand that the weights can be set to 1/2 of exemplar vector and bias can set initially to n by 2 by calculating the unit with largest net input, and the net is able to locate particular unit that is closest to the exemplar. The unit with the largest net input is obtained by the Hamming set using the max net as its subnet. Okay, just see the architecture of Hamming network. This is a conclusion topic. To understand about Hamming network, it's very important. That's enough. This is the architecture of Hamming network. Just see the block diagram first. The structure of Hamming network. Hamming distance matching, max net, blocks you can examine very clearly in the architecture part. First you have to observe the blocks. The architecture of Hamming network is shown in the below figure. Just we examine. Hamming network consists of two layers. The first layer computes the difference between the total number of components and Hamming distance between the input vector x and the stored pattern of vectors in the feed forward path. The efficient response in this layer of a neuron is the indication of minimum Hamming distance value between the input and the category, which is the neuron represents. The second layer of Hamming network is composed of max net, is used as subnet or a winner. Take all network which is recurrent network. The max net is bound to suppress the values at max net output nodes except the initially maximum output node of the first layer. Like this. Testing of algorithm of Hamming network. The given bipolar input vector small x and for a given set of m bipolar exemplar vectors, say E of y, E of j is equal to E of m. The Hamming network is used to determine the exemplar that is closest m the input. Vector x, that a net input entering yj, gives the measure of the similarity between the input vector and exemplar vector. The parameters used here the following: n is equal to number of input units, number of components input output vector, m is equal to number of output units, number of components exemplar vector, E of j is equal to jth exemplar vector, E of j is equal to E1 of j, Ej of j, En of j. Testing algorithm for Hamming net is as follows. Step 0. Initialize the weights for I is equal to 1 to n, j is equal to 1 to m, wij, okay, ei of j by 2. Okay, initialize the bias vector m exemplar vectors for j is equal to 1 to m. Okay, these are all steps for the algorithm because we want to learn perfect algorithm. Okay, perform steps 2 to 4 for each input vector x. Calculate the input for y j. Yn j is equal to some formula. Initialize the activations of MaxNet. MaxNet is found iterate the finding that it is an iterate best matches of the input patterns. Okay, best matches of the input patterns. So this is very important architecture and its concepts of Hamming network. Okay, today I want to stop at this Hamming network part. Make it perfect up to this. They are wonderful concepts. Okay, once again I will revise these concepts in the next class, and I will go to the some sort of other network type. This Hamming network is very important. I given a clear analysis, mathematical analysis, and picture everything to you. Okay, thank you all. Thank you all for the cooperation. Okay. So in the next presentation, again I will recall. I explained each and every wonderful concept. Okay, in the clear manner. Each steps are posted in the chat box, and I explained very simple manner in my presentation. Those concepts what we require, diagram, concept, that's enough. For Hamming network, steps are there, of course. Those steps are mathematical steps. Why these mathematical steps are needed? The mathematical steps are to build a code program. Suppose you want to write any program based on the particular application. Okay, using the Hamming network. Okay, using the Hamming network is used for some particular application. On that time, these concepts will come into the picture. On that time, this it purely application dependent. It's purely application dependent. On that time, all these concepts will come into the picture. Okay, we can note that. Okay, take an application. For that application, Hamming code is perfectly suitable for that application. Okay, how clearly it is suitable for that application? Hamming code. If it is suitable to that application, we want algorithm steps. Algorithm clear steps. That's what I am highlighting. They are mathematical steps, of course. Okay, thank you. Okay, we will continue that with the wonderful concepts in the next presentation. Thank you all.